I want to begin with a confession. I have spent the better part of my life thinking about quantum electrodynamics, nuclear reactors, the far future of the cosmos, and the possibility of life around distant stars. I have worked alongside some of the greatest physicists who ever lived, Feynman, Bethe, Oppenheimer, and yet if you were to ask me right now to give you a truly satisfying explanation of why an airplane flies, I would have to pause. And that pause, I think, is one of the most honest and underappreciated moments in all of science, because the truth is, nobody really knows. Not in the way we'd like to know. Not in the way that lets you sleep soundly at night with a tidy equation tucked under your pillow. And that is a remarkable thing. Every single day, somewhere above your head, hundreds of thousands of human beings are hurled through the atmosphere in metal tubes weighing 400 tons. And the best explanation we have for why those metal tubes don't simply fall out of the sky is contested, genuinely, professionally, embarrassingly contested. Let me explain what I mean and why I think this matters far beyond aviation. The standard story, the one you were probably told in school, the one printed in most introductory physics textbooks, goes something like this. An airplane wing is shaped in a special way. The top surface is curved and the bottom surface is relatively flat. When air flows over the wing, the air traveling over the longer curved top surface has to travel farther than the air going underneath. And because it has farther to go in the same amount of time, it must travel faster. And because faster moving air has lower pressure, this is Bernoulli's principle, the pressure on top of the wing is lower than the pressure below. And that pressure difference pushes the wing upward. Lift problem solved. Let's have lunch. Except, no, that explanation is wrong. Or rather, it is so incomplete that it amounts to being wrong. And the particular wrongness of it is instructive, because it tells us something about how we deceive ourselves with tidy stories when the real situation is far more complicated and far more interesting. The fatal flaw in that story is something called the equal transit time fallacy. The explanation assumes that two air molecules, one going over the top of the wing and one going under the bottom, must arrive at the trailing edge of the wing at the same time. Why should they? There is no physical law that demands this. No reunion is scheduled. No agreement was made. In fact, if you do careful measurements, and people have done careful measurements, the air going over the top of the wing arrives at the trailing edge considerably earlier than its counterpart going underneath. The equal transit time assumption is simply made up. It is an invention of convenience that happens to give a plausible-sounding story, but it is not what actually happens. So if the Bernoulli explanation is wrong, what is the right explanation? Well, here is where things get genuinely interesting. And here is where I want you to resist the urge to reach for another simple story, because the real answer involves holding several things in your mind at once, and none of them on their own is complete. The wing does generate lift through pressure differences. Bernoulli's principle is not wrong. It is just that the reason for those pressure differences is not what the textbook says. The wing is not just shaped in a particular way, it is also tilted at an angle to the oncoming air. This is called the angle of attack. And when the wing meets the air at this angle, it deflects the air downward. It pushes air downward. And Newton's third law tells us that if the wing pushes air down, the air pushes the wing up. That is real, that is happening. But it is not the whole story either. What actually happens at the surface of a wing is described by something called the Kutta condition, named after the German mathematician Martin Wilhelm Kutta, who worked on this problem in the early 20th century. The Kutta condition says that the flow of air around a wing must leave the trailing edge smoothly. It cannot go around the sharp trailing edge of the wing. This condition, combined with the mathematics of fluid dynamics developed by people like Kutta and the Russian mathematician Kutta-Joukowski, gives you the circulation theory of lift. The wing causes air to circulate around it in a particular way, and this circulation, combined with the velocity of the aircraft through the air, produces lift. Now, this is mathematically precise and experimentally verified. It works. Engineers use it. Airplanes fly because of it. But here is my complaint, and it is the complaint of a physicist, not an engineer. The Kutta condition is imposed. It is a boundary condition that we add to our equations because it gives the right answer. We do not derive it from more fundamental principles in a way that is deeply satisfying. We say the flow must leave the trailing edge smoothly. Why? Because if it doesn't, we get infinite velocities, and infinite velocities are unphysical. So we impose the condition that rules out the infinity, and then we get lift But the underlying question, why does air behave exactly this way? What is it about the molecular interactions at the surface of a real wing that produces this elegant circulation pattern? Question takes you into the full turbulent complexity of real fluid dynamics, and there, I must tell you honestly, we are not standing on entirely solid ground. Real air is viscous. Real wings create boundary layers, thin regions of slow-moving air right at the surface of the wing where the effects of viscosity are dominant. These boundary layers can separate from the wing under certain conditions, and when they do, you get a stall. The wing stops flying. The mathematics of viscous fluid flow is described by the Navier-Stokes equations, a set of nonlinear partial differential equations that have been studied for nearly 2 centuries. The Clay Mathematics Institute has offered $1 million to anyone who can prove, in a mathematically rigorous sense, that solutions to the Navier-Stokes equations in 3 dimensions always exist and remain smooth. That prize has not been claimed. The question is still open. The equations that describe the air flowing around a wing in full generality are, in the deepest mathematical sense, unsolved. I find this extraordinary. I find it one of the most extraordinary facts in all of applied science. We build aircraft that carry 800 passengers across oceans. We design wings with computational precision down to fractions of a millimeter. We have sent probes to the outer planets and landed robots on Mars. And yet the fundamental equations governing the flow of air around the very wings that lift us off the ground have not been fully tamed by mathematics. We use approximations, we use simulations, we use empirical data gathered from wind tunnels and test flights. It works magnificently, but it is not in the deepest sense understood. Now I want to talk about what this tells us, not just about flight, but about the nature of scientific knowledge itself. There is a hierarchy in science that we rarely make explicit. At the bottom there is raw empirical observation, things that happen, measured and recorded. Above that there are phenomenological models, descriptions that fit the observations, that allow prediction but that do not necessarily explain. Above that there is genuine mechanistic understanding, knowing not just that something happens, but why, in terms of more fundamental principles. And above that, in rare and wonderful cases, there is what I would call deep unification, the moment when seemingly disparate phenomena are revealed to be instances of the same underlying truth. Flight lives, at the moment, somewhere between the phenomenological and the mechanistic. We can predict lift with extraordinary precision. We can design wings that work beautifully across a vast range of conditions, but the full mechanistic story, the one that takes you from the quantum interactions between air molecules and the wing surface, all the way up to the smooth, elegant circulation of macroscopic airflow, that story has gaps, uncomfortable gaps that most engineers wisely ignore because the approximations they use are good enough and the airplanes fly and life is short. But the gaps are there, and I think we should look at them honestly. Let me tell you something about turbulence, because turbulence is the heart of the difficulty. When air flows slowly and smoothly, it flows in what we call laminar flow, neat, orderly layers sliding past one another. When you disturb it or speed it up or force it around a complicated shape, it becomes turbulent. It breaks into swirling eddies, chaotic and unpredictable at the small scale, though predictable in a statistical sense at the large scale. The transition from laminar to turbulent flow is one of the great unsolved problems of classical physics. We can describe it, we can measure it. We have a dimensionless number, the Reynolds number, that tells us roughly when to expect turbulence. But we cannot derive from first principles exactly when and how a flow will become turbulent, or describe exactly what happens in the turbulent regime without enormous computational approximations. Richard Feynman, my old friend, a man not known for understatement, once called turbulence the most important unsolved problem of classical physics. He said this not to be dramatic, but because he meant it. The mathematics of swirling, chaotic fluid motion has resisted every elegant analytical approach that physicists have thrown at it. We have models, we have simulations. We do not have, in the way we have for electrodynamics or quantum mechanics or general relativity, a deep, clean, complete theory. And yet, and here is the thing I want you to hold on to, aeroplanes fly every day, reliably, safely, predictably. How? The answer is that engineering wisdom and physical intuition, accumulated over more than a century, has built up a body of practical knowledge that works even in the absence of complete theoretical understanding. The Wright brothers in 1903 did not know the Navier-Stokes equations. They knew how to build a wind tunnel, they knew how to measure things. They trusted their observations over the theoretical predictions of the learned men of their time, predictions, I should mention, that were often wrong. Samuel Langley, who was the secretary of the Smithsonian Institution and had a much larger budget than the Wright brothers, built his flying machines on the basis of theoretical calculations, and they fell into the Potomac River. The Wright brothers, who were bicycle mechanics from Ohio with no university degrees, built their machines empirically, iteratively, carefully, and they flew. There is a lesson in that. Not a lesson against theory. I am a theorist, I would not be so foolish, but a lesson about the relationship between theory and practice. The history of flight is a history of practice outrunning theory, of engineers solving problems that physicists had not yet fully formulated, and we are still in that situation today. The computational fluid dynamics used to design modern aircraft wings involves approximations whose justifications are partly empirical, partly theoretical, and partly, to be honest, a matter of long experience and professional judgment. It works, but it works in the way that a recipe works. A skilled chef can make a magnificent dish without knowing the precise biochemistry of the Maillard reaction. A skilled aeronautical engineer can design a magnificent wing without solving the Navier-Stokes equations from first principles. Now, I want to address something that comes up whenever this topic is discussed, because I think it leads to a confusion that is worth clearing up. Some people, upon hearing that the standard Bernoulli explanation is flawed, conclude that we have no idea why planes fly, that it is a mystery, that perhaps physics is just a collection of useful fictions with no connection to reality. This is not what I am saying. Not at all. We have very good understanding of flight. The circulation theory of lift is correct and well verified. The role of viscosity and boundary layers is understood qualitatively and quantitatively in many important regimes. Computational simulations of airflow around wings, while they use approximations, are extraordinarily accurate and have been validated against experimental data many thousands of times. Modern aircraft are not flying on the basis of guesswork. They are flying on the basis of a century of careful science and engineering, and that science and engineering is genuinely impressive. What I am saying is more subtle. I am saying that the deepest mathematical foundations of the theory, the full, rigorous, from first principles understanding, are not yet complete. There are open problems, there are questions that remain unanswered, and I think it is important to be honest about this rather than presenting a tidy, oversimplified story that gives the impression of complete understanding when complete understanding has not yet been achieved. Why does it matter? Because the gaps in our understanding of fluid dynamics are not merely academic curiosities. They have real consequences. They mean that there are flow regimes, particularly at very high speeds, very high altitudes, or in unusual geometric configurations, where our predictive tools become less reliable and we must fall back more heavily on empirical data. They mean that the design of aircraft is not a purely deductive science, but a subtle combination of theory, computation, and experiment that requires careful judgment. They mean that when something unexpected happens, when a new aircraft configuration behaves in a way that surprises its designers, we should not be entirely surprised that we were surprised. I want to say something about the beauty of this situation, because I do think it is beautiful in a particular way. The universe is not obliged to be comprehensible to us. The fact that we can fly at all, that the equations of fluid dynamics, even in their incomplete state, give us enough leverage to build safe and reliable aircraft is already remarkable. The fact that the equations are hard, that turbulence resists our analytical tools, that the Navier-Stokes problem is worth $1 million prize, tells us something about the depth of the universe. It tells us that even in ordinary, everyday phenomena, the movement of air past a curved metal surface, there is more going on than our current mathematics can fully capture. Heraclitus said that nature loves to hide. I think he was right. But I would add that nature also loves to tease. It shows you just enough to make you confident, and then when you reach for the next layer of understanding, you find that the ground shifts slightly beneath your feet. The Bernoulli story seems complete, and it is not. The circulation theory seems rigorous, and it rests on an imposed boundary condition. The Navier-Stokes equations seem fundamental, and they resist solution. Each layer of understanding reveals a deeper layer of mystery, and I find that not discouraging but thrilling. It is the fundamental character of science. Let me come back to airplanes one more time, because I want to give you a feel for the physics that is real and that does explain in a genuine way how lift is generated, not the false Bernoulli story, but something closer to the truth. When a wing moves through air, it does several things simultaneously. It deflects air downward. This is momentum transfer, pure Newton. The reaction to pushing air down is a force upward on the wing. This is real and measurable and accounts for a significant portion of lift, especially at high angles of attack. It also creates a pressure distribution around itself, high pressure below, low pressure above, and this pressure difference integrated over the entire wing surface is the lift force. This is Bernoulli's principle correctly applied. The velocity distribution around the wing creates a pressure distribution, but the velocity distribution is not what the textbook says. The air over the top does not travel faster because it has farther to go and must meet its partner at the trailing edge. It travels faster because the shape of the wing, combined with the angle of attack and the Kutta condition, forces a particular circulation pattern onto the airflow. The mathematics of this conformal mapping complex potential flaw, the Kutta-Joukowski theorem, is genuinely elegant and worth knowing. The Kutta-Joukowski theorem says something beautiful and simple. The lift per unit span of a wing is equal to the density of the air times the velocity of the aircraft times the circulation of the flow around the wing. Lift equals rho times v times gamma, where gamma is the circulation. This is exact for an ideal fluid. It tells you that to generate more lift, you can go faster, which is why planes need runway speed before they can take off, or you can increase the circulation, which is what flaps and slats do when they change the shape of the wing at takeoff and landing. The engineering of modern high-lift systems, those remarkable unfolding leading-edge slats and trailing-edge flaps that transform the wing profile during takeoff and landing, is a direct application of the Kutta-Joukowski theorem.
Increase the circulation, increase the lift. And yet even this beautiful theorem is derived for an ideal inviscid fluid, a fluid without viscosity. Real air has viscosity. Real wings have boundary layers. And the circulation itself, the gamma in the equation, how do you calculate it for a real wing in real air? You need empirical data, or you need computational fluid dynamics, or you need experimental measurements in a wind tunnel. The clean theorem connects to messy reality through an interface that is partly theoretical and partly empirical. That is the honest state of affairs.
I have been privileged in my life to know many brilliant people, and one thing I have noticed about truly great scientists is that they are comfortable with this kind of honest incompleteness. They do not mistake their models for reality. They know that a model that works is not the same as an explanation that is final. They hold the map and the territory separately in their minds, and they are not troubled when the map turns out to be less detailed than the territory. The trouble comes, in my experience, when people mistake the map for the territory, when the tidy story in the textbook is taken as a complete account of nature rather than as a useful approximation to a reality that is richer and stranger. The great physicist Paul Dirac once said that it is more important to have beauty in one's equations than to have them fit experiment. He said this in a particular context about a particular kind of theoretical work, and I do not entirely agree with him. But there is something right in what he said. The pursuit of mathematical beauty, of deep and elegant structure, has again and again led physicists to genuine truth. The Navier-Stokes equations are beautiful. The Kutta-Joukowski theorem is beautiful. The open problems in fluid dynamics are not embarrassments. They are invitations. They are the universe saying, there is more here, come and find it. We have been flying for just over a century. The Wright brothers made their first powered flight in December of 1903. In the span of a single human lifetime, we went from that 12-second, 12-meter hop at Kitty Hawk to landing human beings on the moon. The progress has been extraordinary, but the understanding has lagged behind the achievement, and that is not a failure. That is the normal condition of science in contact with the real world. We do first, we understand later, and the understanding is always incomplete, always pointing towards something deeper. So the next time you are sitting in an airplane, perhaps a little nervous, as even the most rational people sometimes are, and you feel the wing flex slightly in turbulence, and you wonder whether the thing holding you up is truly understood, you can take comfort in two things. First, practically, the aircraft was designed by people who have accumulated a century of empirical wisdom, who have tested their designs in wind tunnels and in flight, who have safety margins built upon safety margins. The plane will almost certainly land safely. Second, intellectually, the phenomenon keeping you airborne is one of the genuinely interesting open problems at the edge of applied mathematics and physics. You are being transported across the sky by a force that humanity has not yet fully explained. That is not a reason for alarm. It is, if you are the right sort of person, a reason for wonder. I have always believed that the proper response to genuine mystery is not anxiety but curiosity. The fact that the universe contains depths that our current understanding has not yet penetrated is not a sign that we are failing. It is a sign that the universe is worth studying, that there is always more to know, that the work is never finished, and that is, to my mind, a magnificent thing. Thank you.